for the opportunity to speak here. It's really great to be here in Moscow. I'm going to be talking today about the cosmic microwave background, the afterglow of the hot Big Bang, and what it can tell us about our universe. In the first part of my talk, I'll try to explain why the cosmic microwave background is the clear smoking gun evidence that tells us why the Big Bang happened, or it proves that the Big Bang happened. In the second part of my talk, I'll discuss some current research in this area. Let me start, though, by reminding you where we are in the universe and giving you some background. I'm sure you all know about this, but, our planet is orbiting around a star, the sun, but it's not the only star, even in our galaxy. In our Milky Way galaxy, there are 300 billion stars, just like our own star. And each star, typically has a planet. So there are lots of stars in just one galaxy, our Milky Way galaxy. But our galaxy is not the only galaxy in our universe. Over the past decades, we've seen a huge number of galaxies out there, each of which contains hundreds of billions of stars. And I think the best way of showing this is to just show you data. So here is a real observation, and here is a video made from these real observations. So here you can see a video made of flying through the distribution of galaxies. Each image is a real picture taken of a galaxy, and each position is a real galaxy position. Right? So you can, and of course, to remind you, each galaxy has hundreds of billions of stars, just like our own. So the takeaway message is that there are a lot of galaxies out there, and the universe is really big. But what was a very, very surprising discovery is not just that there's a large number of galaxies, but that all the galaxies are moving away from us. Okay? So the universe is not stationary, but every galaxy we see is running away from us. And in fact, the further away the galaxy is, the faster it's running away from us. Right? Now, this was a really surprising discovery made by Hubble a long time ago. And what does it mean, right? Does it mean that we are particularly terrible and everyone wants to run away from us? That's not the current interpretation. So the way that we explain this is by realizing that space itself is expanding. Okay? And that explains what we see, because the more space is between two galaxies, the more rapidly the space is expanding. The more the space is expanding, and so the faster the galaxies seem to be moving away from us. Okay? So to illustrate that, imagine each of these blue dots is a galaxy, and we live on this galaxy here in the middle. Now, because all the space is expanding, you'll see that this distant galaxy up here seems to be moving away faster than the nearby one, just because the space itself is expanding. So you'll see the far one, if I start expanding space, is running away faster. But it's not that we are particularly terrible. It's just that every galaxy is moving away from every other galaxy because space is expanding. Right? Okay, so the explanation for what Hubble saw is that space itself is expanding. But this, if you think about it, leads to a very surprising conclusion. Because if you think about all the distances getting bigger and bigger with time, you could now imagine running a video of the universe backwards, right? if everything is getting bigger with time, there must be a time when everything was really close together, right? Where all the distances go to zero, right? Now, this doesn't mean that there's one center of the universe. It just means that all the distances get very small. And if in the early universe everything was really close together, that also means that the early universe was really, really hot. Right? And you can understand this if you're compressing like a gas. It gets really hot. If you've ever inflated a bicycle tire, you know this. So the early universe, based on this observation that space is expanding, people proposed and inferred that the universe began in a really dense and really hot initial state. And this incredibly dense, incredibly hot initial state we call the Big Bang. All right? And now I want to explain how we know that the Big Bang happened and explain why the cosmic microwave background is clear evidence that the Big Bang happened because we can basically see it. Okay, so let me explain why the Big Bang predicts the cosmic microwave background. So the early universe, I've said, is incredibly, incredibly hot and dense. Right? It's so hot that the protons and electrons can't be held together to neutral atoms. They're moving around very quickly, and this is a state of matter we call a plasma, right? So things are so hot that they're like the inside of the sun, or like, fire. All right, so that was what it was like everywhere in the early universe, because it was so dense and hot. But then, over time, space got bigger, the universe expanded and cooled. And even though in the early universe, it was a glowing hot plasma, right, with the blue here showing the glow, the light of this hot plasma, if you wait long enough in this Big Bang model, eventually the universe cools to the point where suddenly, from electrons and protons, neutral hydrogen atoms can form. And these are transparent. And so the glow, the heat radiation from this hot early universe suddenly can escape and travel to us. Right? So let me show a video showing this. Right? So here you see the really hot early universe. The blue shows the light from this glow, and red shows protons, and green shows electrons. The universe cools and suddenly becomes transparent. And the light, this sort of afterglow, then escapes and travels through the universe for billions of years past the formation of the first stars and galaxies for a very, very long time until eventually it reaches us on Earth. At least this is what the Big Bang model predicts should happen. Okay? So, to remind you, this Big Bang model, because the early universe is a glowing hot plasma, almost like a sea of fire, even if it cools later, the light should still be left over and should still travel through the universe until it reaches us. So that is a clear, unavoidable prediction of having a Big Bang and having a glowing hot early universe. There's actually another way of thinking about this, though, that I think is very interesting, which is that people often think cosmologists speculate about the past. But that's not true. We can see the past. And the way to think about this is the following. Even if you look on the other side of the room, you're not seeing the other side of the room now. You're seeing it a little bit in the past. right? Because the light from over there takes a few nanoseconds to reach your eye, has to travel to you. If you look at a star that's really far away, you're seeing the star maybe a few million years in the past because it's taken a very long time to travel to us. So now you could imagine looking all the way out as far as you can see into the darkness. And if you look as far as you can see, eventually you'll look so far back in time that you see the glowing hot Big Bang. Okay, and that's another way of thinking about the CMB. So we've just looked so far out and so far back in time that we've seen the primordial fireball. Okay? But in any case, the takeaway message is that the Big Bang Theory makes a clear prediction. If we look out into the sky, we should see light from the primordial fireball. Now, you may have noticed that if you go out at night and you look into the night sky, you do not see a sea of fire, right? Unless something has gone very wrong. Right? It's a dark sky. You don't see, glowing hot plasma. Why is that? Well, the reason is that the light has been stretched. Okay? So even though we could have seen it in the early universe, the expansion has stretched out this light so that our eyes can't see it anymore, because the light has been stretched from visible light to microwave radiation. Sadly, our eyes can't see in microwaves, but you can build microwave eyes, right? You could build a microwave telescope and look at the night sky, and you should then see this afterglow light from the hot Big Bang, right? This cosmic microwave background. And this is what scientists did more than 50 years ago by accident, right? So there was a group in Princeton that thought that you could find this cosmic microwave background, and they started building a telescope. But then they realized that another group had accidentally found this cosmic microwave background. All right, and the group that accidentally found it was a team of Arno Penzias and Bob Wilson at Bell Labs. And so why did they discover this microwave background, this afterglow? Well, they were basically just trying to get their telescope to work. And they couldn't get it to work. So they built this Holmdel-Horn antenna, which they wanted to use to do astronomy, but also to test communications equipment. And they were very good experimentalists. They spent a lot of time designing it, but it just didn't work right. Okay? They always had this noise that was preventing the telescope from working properly. Okay? And so they tried everything to get rid of this noise that was limiting their measurements. So I think, they tested every component of this telescope. They tried to make sure that it wasn't radio interference from New York City. Then there's a famous story that they were worried that pigeons were nesting here and leaving droppings that were radiating microwave noise. So they trapped the pigeons and got rid of the pigeons, but still they couldn't fix the telescope, right? There was always this excess noise. I used to always hear the story with them trapping the pigeons, but there's actually a dark side that I recently found out, which is that the traps didn't work, and one of them had to buy a shotgun and shot all the pigeons because he was so frustrated that the telescope wasn't working. Okay, But eventually they realized that it wasn't pigeons and there wasn't a problem with their telescope. And the noise they were seeing was not noise, it was a signal from the early universe. It was this cosmic microwave background radiation that's predicted by the Big Bang model. Right? And so what they found is that there's radiation coming from the night sky, and it's coming from everywhere. And that's what this very simple diagram is showing. What I've done here is I've taken the night sky and I've unfolded it and projected it onto this slide. Right? And the fact that it's green everywhere is supposed to tell you that basically there's the same brightness. They found the same brightness coming from all the directions they looked in the sky. Okay, so they reported this, and that was pretty good evidence that, yes, the Big Bang happened. But scientists are very stubborn, and so some scientists, such as Hoyle in Cambridge, actually, said, no, this is some other light. It's not the microwave background. And so the way it was definitively proven is that because the microwave background is just the glow of a hot plasma, it should have a certain kind of color. It should be just like when you heat up a piece of metal, or you heat up a piece of metal, it starts to glow, right? It's a characteristic glow radiation called black body radiation. And so the question was, is the CMB is it producing black body radiation? And so the prediction of the CMB is shown in this solid line here. And over the next decades after this discovery, people made better and better measurements of the spectrum, which tells you the brightness as a function of frequency, or sort of the color, and the data points of an experiment in the early 90s are shown here. And you can see this is a pretty good agreement, right? In fact, it's an almost perfect match to the Big Bang model, the black body spectrum prediction. The error bars have been blown up by a factor 200, right? So this is an incredibly precise confirmation that this radiation from everywhere in the sky that we're seeing is indeed the afterglow of the hot Big Bang, as predicted by the Big Bang model. It is the cosmic microwave background. Right? So this is definitive proof that the Big Bang happened. We can see its light. Okay. So hopefully that was pretty convincing that, we know the Big Bang happened because we can see it. Now, let me talk about what else we've learned from observations in the CMB, and in particular, from patterns in the CMB. So to motivate that, you can ask the question, we have seen this cosmic microwave background radiation from everywhere in the sky, and at first it seemed like this was uniform, that from every direction it was equal in brightness. And so that's weird because the current universe is not the same everywhere. So people tried to increase the contrast, right? And see if it was still the same everywhere. So they increased it by a contrast of 1,000 over a few decades and still found nothing. It was the same brightness in this direction as in this direction at the level of a part in 1,000. Until finally, in the early 90s, a few experiments, including the probably most well-known, the Kobe experiment, although there were also a Russian experiment, I believe, finally turned up the contrast by enough, by a factor 100,000, that they saw for the first time differences in the brightness of this cosmic microwave background radiation. So what this plot is showing you is the brightness of this afterglow as a function of where I'm looking on the sky. Okay? And where it's red, it's a little bit brighter And where it's blue, it's a little bit less bright than average. Right? So there's features in this Big Bang fireball that we're seeing in the early universe. Yep. Yes. That's right. Well, because we can't see it with our eyes, we have to map the sort of microwave color to a real visible color for us using a color scale. But this is an actual picture. Yeah. If you had microwave eyes, you could see this. Yeah, feel free to interrupt me if you want. That's great. Well, basically, we know how to measure the brightness. We have a device that measures the brightness in microwave as a function of where I point. Okay? So what you do is you go around the sky and you look at every point in the sky and you write down how bright is it. And then you plot that on one of these figures. Right? And we've gotten very good at doing this. After Kobe, another satellite was sent up and took a better image, right, with seeing much smaller and finer features. And then recently, over the last 5 years, we've had observations from the Planck satellite, as well as better ground-based telescopes. And so now we're at the point where we have a beautiful, sharp image of nearly all the features in the brightness of the CMB. And here is the picture of the microwave background. Again, this is an actual picture of the light from the early universe. You can think of it as sort of the surface of the Big Bang fireball. All right, so here it is. All right, and again, where it's red, that's a direction where it's a little brighter, and where it's blue, that's a direction where it's a little bit less bright than average. But yeah, just again to emphasize, this is an actual picture of the past. It's a picture of the universe as it looked 13.8 billion years ago, very soon after the Big Bang. Okay? Right, and just to remind you again where this comes from, I think I've said this, the afterglow travels through the universe, hits our telescope, and then we make a map of the brightness that's all around us. Okay, so here it's sort of illustrated the setup. Right? Okay. Good. Now, we've seen these fluctuations, these patterns in the brightness. Why are they there? What are these things that we're seeing here? Now, why are there some brighter regions, some brighter directions, and some that are less bright? Well, the simple explanation is that in some regions, there's a little bit more matter. And these regions with a little bit more matter have more photons and so appear brighter. Okay, so these patterns, these fluctuations in the brightness correspond to fluctuations, differences in the density in the early universe. Now, why is this important? Why is it important that we've seen these patterns? And why is it important that we've made these observations? Well, first of all, it's important because it allows us to understand the evolution of the universe. And here's sort of how that works. Say you look at the CMB and you see a red spot. That means it's bright. It's bright because there's more matter than average, okay? And you can ask, what happens to a place where there's more matter than average? Well, it has more gravity than average, and so it pulls in even more matter, and that then kind of collapses, falls inwards to be more dense, and then it has even more gravity, and it pulls in even more stuff. And you have this runaway sort of infall, runaway collapse that eventually forms a galaxy and forms stars and planets and people. Okay? So seeing these patterns is important because this is a picture of the past, right? This is a picture of the universe 13.8 billion years ago. And so it's kind of the baby picture of the universe. We can understand how these, a bright spot in the CMB, sort of because there's more matter, grew over billions of years into galaxies and stars and planets and people. In fact, we can even do simulations of how this works. So here I'll show you a simulation of us starting the early universe in a nearly uniform state, but with a little bit more stuff in some directions, corresponding to what we see in the CMB. And then you just wait and let gravity work and let gravity form galaxies and structures. Okay, so it starts off uniform, and then gravity causes this infall, this collapse. And at these sort of structures are going to form galaxies. Okay, so start off uniform. This is what the uniform stuff, almost uniform is what we see in the CMB, but this directly turns into our universe today. Okay, so it's important because it's the baby picture. We can understand how it relates to what we see today. So that's the first reason it's important. Now, if you think that explanation is a bit unsatisfying, I kind of agree, because now we have another question, which is, well, we've understood galaxies come from these small fluctuations we see in the CMB, but where did the fluctuations come from? Okay, now there's another question. I will talk about this later at the end of my talk. Okay, so the first reason that seeing the patterns in the CMB is important is because it allows us to understand the evolution of the structure today from the beginning. But the second reason these patterns are important is because we can use them as a tool to understand, to learn about the properties of our universe. Okay? And these measurements have gotten so good that we can make percent-level measurements of the composition of the universe, the age of the universe, and the geometry of the universe, just based on how these fluctuations, how these patterns appear. All right, let me show you sort of how that works. With an example, which is, say you want to figure out the size of the universe based on the patterns in the CMB. Okay? Now, we can calculate the physical true size of the patterns. I can take questions on that, but I'll just say it now. We can calculate the physical size of a typical spot, like a typical feature in the CMB. And now you can figure out how far away the CMB emission surface is by just looking at how big it appears. Right? So if I know the size, if a feature looks very big in the sky, you know the CMB was emitted nearby, and then you know the universe is very small. If the feature appears very small, then you know the CMB was emitted very far away, and the universe is very big. Okay, so you can sort of look at what you see and kind of match it to a close CMB, a far CMB, or one that's in the middle. So from the appearance of the patterns, in this way, we can determine the size of the universe. Okay? Right, any questions? Okay, we can save them until after too. All right. This is not actually very precise if you just sort of look at a map and say, oh, well, it looks pretty big to me. So how do you do this quantitatively? How do you do this precisely? Well, this is a technical slide, so don't worry if you don't understand it. Basically, we measure a quantity called the power spectrum. And so in blue are the measurements of the power spectrum this map. And this power spectrum tells us, the magnitude of the patterns as a function of how large they appear on the sky, how large the angle is that they span in the sky. Okay, so you can take this map and write it as this power spectrum, and that's shown in blue, magnitude of fluctuations as a function of angular size in the sky. Right? And then we can make theory calculations of how this power spectrum should appear depending on the size of the universe, for example, or depending on the geometry of the universe or the composition of the universe. And so we can kind of play around with this theory model until we get something that looks just like the data. And then we can look up, oh, this is the age that we needed to make it look like the data. Okay? And so that's how, from our measurements in blue, coupled with a very good theoretical understanding of the CMB, we can learn a huge amount, right? We can learn an enormous amount about not just how structure formed from small initial fluctuations in density, but we can also learn about the age of the universe from the patterns in the CMB. 13.798 plus or minus 0.037 billion years, right? We know it pretty well. The geometry of the universe, space is flat. The composition of the universe. Okay, let me talk about what we know about the composition of the universe, what the universe is made out of from the CMB. Okay, from the CMB power spectrum, from the CMB patterns, we know very precisely that the atoms, normal matter made out of atoms, is actually only 5% of the universe, of its energy. Okay, so only 5% of the universe is made up of normal atoms. And, whether that's gas or galaxies or stars or people or anything, only 5%. Nearly 25% is made of something that's kind of strange, which is dark matter. We know this from the CMB. What dark matter is it's like normal matter, but invisible. Okay? So it's stuff, a substance that we cannot see, but we know is there because it has gravitational pull. Okay? And we know it's there not just from the CMB, but also through many other methods and many consistency checks. So we know for sure that most of the matter is dark matter. Right? And we know it's 24%. But dark matter is not the weirdest thing that we think is going on in the universe. The vast majority of the energy in our universe, we believe, based on the CMB, based on ultra-high precision CMB observations, is dark energy. Now, dark energy is, I think, much stranger than dark matter. I don't think dark matter is that strange. Different kinds of particles feel different forces, so it's not that weird that some maybe don't feel electromagnetic forces and so are not visible. I don't think that's that weird. But dark energy, I think, is really weird. So dark energy is a form of energy that's not pulling things together like normal matter and normal energy, but it's pushing out. It's accelerating the universe apart. All right, and so that's as weird as if you throw up a ball and, instead of sort of slowing down and coming back to you, maybe it slows down at first, but then it shoots off really quickly. So it is very weird behavior that this dark energy seems to cause. And it also is a bit depressing because dark energy is the main part of the universe now. And what it's going to do to the universe in the future is accelerate it apart faster and faster and faster. And so in the far future, everything will be very empty and very dilute and very depressing. So it's not that great. Okay, so but we figured this all out from the CMB. I think it's well summarized by a very silly English tabloid newspaper headline. It's very sensationalistic, but it's actually totally true. Okay, so this is an actual headline. And yes, that is technically true, but you shouldn't worry because it'll happen in 50 billion years. So, no, this is actual real news. This is just silly real news. Yeah, so if you're worried about 100 billion years in the future, then you should think about this. Okay, so from the patterns in the CMB, we've learned a huge amount about our universe. We've learned that on the one hand, we live in a very simple universe, right? Where you can simulate, put it in a computer, and predict everything, right? Based on just 6 numbers that describe, for example, how much atoms do I have? How much dark matter do I have? How much dark energy do I have? And we know these numbers almost perfectly from the CMB. So we know exactly what the universe is made out of. We know exactly the age of the universe. We know exactly the size of the universe. We can see all the way back until almost the Big Bang, and we can understand how the primordial universe related to our universe today. So as cosmologists, on the one hand, we should be incredibly happy, right? Because we've understood almost everything. But on the other hand, if you're really honest about it, or you look at the comment section of this article, then you see people who, take different points of view, right? And they say, come on, 70% of the universe is made of something that we don't understand, and then 30% is something else that's weird, and somehow that's going to blow up the universe, and that just sounds like nonsense. So that isn't really true, but there is sort of a point, which is on the one hand, we do know a lot, and we figured out an enormous amount, but in some sense, we've just figured out how little we understand, okay? And we've put a number on how much we don't understand, right? That number is 71.4% plus 24%, which is, I think, 95%. Okay, so we've understood how little we know, which is good. And that brings me to my final section of the talk, which is what don't we understand and what are we trying to understand now and are working on now with the cosmic microwave background. And so there are, I think, 3 big questions that we in cosmology need to understand. The first question, which I won't talk about, is what is dark energy? A lot of people are trying very hard with theory and observations to understand this. I won't talk about that. I will talk about 2 of the big other questions. What is the dark matter and where is it in our universe? And I will also talk about trying to understand what happened at the very beginning of the universe, before the CMB, at 10 to the minus 32 seconds, right? Some incredibly tiny, incredibly early time. All right, let me start by what I'm working on now, which is sort of what and where is the dark matter. Now, in particular, what I'm trying to do is map the dark matter because that could tell us about its properties, okay? So how do you map in something that you can't see? Okay, so it's hard to figure out where something is that you can't see. And so the way we do this is through an indirect effect. Because even though dark matter we can't see directly, it does have gravity. And this gravity affects how the CMB travels through the universe. Okay? So let me show you this. The CMB is emitted a long time very far away, and it travels to our telescopes, but along its path, it gets gravitationally deflected by all the dark matter through which it moves. And this leads to a characteristic extra pattern that's added to the CMB pattern. Okay? So what you should imagine here is that I have a very big clump, a big structure of dark matter that I've placed in front of the CMB. And even though you can't see the dark matter directly, you can see its effect on the CMB. Because the light is bent around this clump of dark matter, just like a magnifying glass, right? And that magnifies the background CMB. So hopefully you can see there's this stretching pattern, sort of stretched out compared to out here, out here. And so what I work on is sort of looking for these stretching patterns in the background CMB and using them. If I see one of these, we know there's a big structure of dark matter. And so we can take our CMB maps and make maps of all the dark matter in the universe. Okay, so here's a map that I made of the dark matter. So in particular, the color scale tells you how much dark matter do I have in a certain direction. Okay, so this is sort of a map on the sky about this big, and each point in this map is some direction in the sky. And soon we'll have a map of basically everywhere. So over the next 5 years, we will make maps of the dark matter like this one, where how light the color is tells you how much dark matter there is over, the entire sky. So we're working now on mapping all the dark matter in the universe. And this is going to be really interesting because we can use that to check, does it look the way we expect? Okay? What the dark matter is will influence how it sort of clumps and what structures it forms. All right? And there's also other reasons to do this, which is that this lensing is a problem if we want to see the early universe, and we need to get rid of it. Okay, so that's the first topic of current research I wanted to focus on, that we're trying to understand what the dark matter is and how it's distributed. Yep? Yeah. No, it's not bad. I think in English, dark doesn't have the sort of negative. It's just invisible, right? But you can see it indirectly through its gravity, right? So you can figure out it's there because it's pulling on you and it's pulling on light. So you can't see it. It doesn't scatter light. It doesn't emit light, but it pulls on you and it pulls on light as it travels past. So that's how you know it's there. Okay, let me now come to the final section of my talk, discussing current research with the CMB that tries to understand what happened at the very beginning of the universe, which we still don't really know. Now, in particular, you can ask related questions, which is, first of all, what blew up the universe and made it very large and very smooth and very flat in the very beginning? But on the other hand, even though something might have blown up the universe, what still made it not totally uniform and flat? So it's almost uniform early on, but we know from the CMB that there are small differences in the density, that in some places in the universe there's there was a little bit more stuff. And in some other places, there was a little bit less stuff. So the other question about the beginning is not what blew up the universe, but what made these small fluctuations, these small differences in the amount of matter I have here compared to here. Now, for both of these questions, what blew up the universe and what made the fluctuations, we have a very good theory, okay? And this theory is called cosmic inflation. All right, let me try to explain what cosmic inflation is. The basic idea is that you can propose the existence of a certain substance, and if you work out what it does is it blows the universe up exponentially fast. Okay? It sort of has negative pressure. It blows the universe up, a billion times in a tiny fraction of a second. Now, how exactly you do this, there are many different ideas, different kinds of substances you could imagine, what exactly the properties are, etc. But the general idea is just exponential expansion. Now, that explains how the universe gets big and flat. But after people proposed inflation to explain why the universe is big, they realized that it actually explains why there are these fluctuations, why there are small differences in how much stuff I have in one place and the other place. And I think it's a really, beautiful idea, okay? And the idea is that this rapid expansion connects the small microscopic world governed by quantum mechanics to the large, real, macroscopic world of our universe. Okay? So let me first explain what I mean by the strange microscopic world of quantum mechanics. Now, in quantum mechanics, the key idea is that there's always uncertainty that you can't avoid. Okay? So there's some degree of randomness that's always there. And so even if you look at empty space, it's never really empty. There are always small random fluctuations in how much energy I have. If I look very closely, if I look on a very short time and a short distance. And let me show you a simulation of empty space in quantum mechanics. So this is empty space if you look very closely in quantum mechanics. Okay, what's plotted here is sort of the energy. I can't get it to blob around again. Come on. Oh. Right, well, you saw what happens. There's just random fluctuations in the amount of energy I have that sort of come in and out of existence, even in empty space. And it's because of this unavoidable randomness. Now, normally, we don't notice this at all, okay? So this happens on really, really small scales, and we don't notice this. But now, when inflation happens, it takes one of these microscopic, invisible, unimportant quantum fluctuations in the vacuum, and it blows this random fluctuation up by a billion times and makes it real, okay? It makes it the size of the universe. And this is the origin. This random fluctuation in the energy and in the matter is the origin of these fluctuations we see in the CMB. Okay? So inflation blows up incredibly quickly. One of these random quantum fluctuations makes it into a real difference in how much density, how much matter I have at a certain point. We see that in the CMB, these small differences in density. And so quantum fluctuation gets blown up, shows up as a bright spot in the CMB, and then over billions of years, falls inward, collapses to form a galaxy. Okay? So the amazing idea of inflation is that, we are here, our galaxy is here, because there was a random quantum fluctuation in the vacuum 14 billion years ago that got blown up and became a real object in the universe. Now, I think this is really cool. It probably sounds very speculative and made up to you, but we actually do have good evidence that this is what happened. And I can go into more detail in questions, but if you think that the origin of these fluctuations is quantum random fluctuations, then you can predict lots of properties that these fluctuations have. They should have a perfect Gaussian distribution. They should be nearly, they should have a certain shape in the power spectrum, which is the shape shown by this red curve. They predict a nearly flat universe, which is what we see. So there are lots of predictions that inflation made that we've tested and have confirmed. Okay, so there is a lot of evidence for this maybe somewhat strange idea that quantum fluctuations were the seeds of all the structure in the universe. But there's one prediction that we have not yet confirmed and not yet seen. And this is what we're working on right now. Okay? And so this prediction is that inflation is so violent and fast that it should make gravitational waves, waves in space-time itself, that show up. Oh, is there a problem? Okay. Okay, let's just pause for a second. Let me know. Okay. Yeah, so why don't we ask a question?
1 second. How did we count age of 380,000 years before CMB? Thanks.
Yeah, that's a good question. Basically, the early universe is a plasma, okay? And in a plasma, there are sound waves, right? Like ripples on, like if you have a lake, there's like a ripple that travels outwards. So we can sort of see how far this ripple has traveled, and that tells us how long, how long the time has been since the beginning. Right. Do you want to take more questions, or are we waiting for a translation? Okay.
I write think about Big Bang. The Big Bang was in everything. Хорошо. Я правильно поняла, что взрыв происходит в каждой точке, а не только в одной, потому что...
Oh, dear. Okay.
Наоборот.
It's very loud. Sorry, Big Bang in... Yes. Right? So remember, a lot of people think of the Big Bang as there was one point from which everything exploded outwards. And that's not the right way to think about it. The right way to think about it is just in terms of distances, okay? All the distances between every object became zero. But that doesn't mean that there's a middle, right? If it's very large, all the distances can go to zero without there having been one point from which it exploded. All right, should we continue with the main talk, or? Yes. Okay. It's the CMB. Actually, 1% of your television static is the CMB, so it's actually not totally wrong. Should we keep going? Okay, all right. Sorry to all of you. I'll try to speak extra slowly or something. Okay. Right. So, as I was saying, there's one prediction that we have not yet seen. The fact that inflation should make gravitational waves that show up in the CMB as a characteristic B-mode polarization pattern. What this means is that inflation predicts these characteristic vortex-like patterns in the CMB polarization. And so if we can find these patterns, we will have confirmed that inflation took place and that inflation is the origin of all the structure in the universe. These quantum fluctuations are the origin of everything. So we really want to find these patterns. They're the smoking gun evidence for inflation. And we want to find them not just to prove that inflation is the correct theory, but also to understand its physics and the physics of the early universe in more detail. And so, if we measure the strength of this inflation B polarization signal, we can figure out which of the different ideas and the different models for inflation is the correct one. Okay, so all of these lines are different ideas for how inflation could work and how the physics of the early universe could work. Right, so if we measure these B polarization signals, we will, first of all, confirm that inflation happened and is the origin of all the structure. And second, we can figure out what kind of physics caused inflation. Okay, so this is why it's a main effort in current CMB research. Now recently, a few years ago, we thought that we had found these B-mode polarizations. Not me, but another group. The BICEP-2 experiment claimed that they had seen these B-mode polarization patterns from inflation. But in fact, it turns out they had made a mistake in removing contamination from our galaxy. Okay, so our galaxy also makes B-mode polarization at some level, and you need to clean it, but they didn't do it right. And so it turned out they just saw our dust in our galaxy, which was very sad. But over the next decade, there's a very strong experimental effort that will probe these B-modes at new unprecedented precision. So let me show you some of these experiments that I'm involved in. Here you can see the Atacama Cosmology telescope. Right here's the telescope in the middle, and the CMB goes in here, bounces around, and we can make maps of the polarization and look for B-modes. And soon we'll have an even better one, the Simons Observatory, that's 100 times more sensitive. It's a big array of nearly 10 telescopes that we're building in the Atacama Desert right now. Right? And so I think it's going to be really exciting in the next 10 years because we may well be able to find these inflationary B-mode polarization signals and confirm inflation and understand its physics. Okay, so let me wrap up. I hope I've convinced you that we've learned, on the one hand, a lot from the CMB. We figured out the age of the universe, the composition of the universe, the ultimate fate of the universe, and we've understood how our galaxy and how stars formed from the initial seeds of structure that we see in the CMB. But we've really just understood how little we know, right? And so there's a lot we still have to understand, answering important questions such as what is dark energy, what is dark matter, and what happened at the beginning of the universe. And I don't know what the answer is to any of these questions, but I'm sure that the CMB will continue to give us lots of new insights and lots of new understanding. So thank you. How are we doing? Great. Okay. So should we take some questions then?
Thank you for a very interesting lecture. First of all, it's very nice to hear, and I think the answer will be 42.
Okay.
From the Hitchhiker's Galaxy.
But what quantity is 42?
Your lecture is very interesting, but it's very complicated for me. But I have one simple question.
Okay.
Was American astronauts on the moon or not? I think you have this secret knowledge. Thank you.
If they weren't, wouldn't the Russians have told everyone that they weren't? Wouldn't you have said? But I don't know. It's not in the CMB, so I don't know.
Поднимайте, пожалуйста, руки, чтобы я видел, кому подходить с микрофоном.
Hello, I think I have a very common question, and I would like to ask the one interesting thing. According to mentioned above, does my atoms and space on it expanding right now?
Yeah, that's a good question.
And why don't I have distortions of my body?
Right, that's a very good question. Basically, whether you're expanding or not depends on whether you're mainly influenced by sort of the gravity of your surroundings or the gravity of the entire universe, okay? And so if you're in a very dense environment, that is the main source of gravitational evolution. And so none of us, well, I don't know, maybe I'm expanding, but we are not expanding, right? Due to the evolution of the universe, right? We're influenced by the Earth's gravitational pull and the sun's gravitational pull, and the universe is totally irrelevant. Only if you're, in a very, big region with very little density on very large scales does the cosmological expansion really determine what happens to you. So, no, we're not. No one is, our atoms are not sort of being blown apart.
So does it mean that gravitation's opposed the expanding force, right?
Yeah, I guess sort of in our region, our gravity is sort of causing, is preventing the expansion. Yeah.
Thank you.
Thank you. Okay, it works. So, what could be the alternatives of these 24%? What could it be? What the alternatives of dark matter? And like you show a map of dark matter, and you said like white spots are where the dark matter is. Is it like inside joke? Why dark matter is with white spots?
No, that was me being dumb about plotting. Yeah, basically, I made a plot of how strong the lensing is. Okay, and the strength of lensing, tells you about how much dark matter there is. So that's why I made that color scale. But that's a good point. So what are the alternatives to dark matter? Well, there are some. I think they're a bit silly. I think there's good alternatives to dark energy. So I think a lot of people say, well, maybe there is no dark energy, but maybe our theory of gravity is wrong. Okay. And so I think for dark energy, that's a plausible explanation. But for dark matter, we have so many different lines of evidence that show there has to be this substance that doesn't interact except for mainly through gravity, right? So we don't just have the CMB. Okay, let me give you a few examples. So one way that we know that it can't be just the wrong theory of gravity is because we can see that if you have two objects that sort of collide, the gas stops, but the dark matter that we probe through lensing kind of sails through. All right, so we know it's kind of a particle, right? It's an independent substance that's not part of the gas. That's one way that we know it's sort of a particle. I think the cleanest way that we know there has to be dark matter is just in how we get from the CMB to the galaxies. Okay, so if you look at this video here, I have to go back a little while. Sorry. Remember, there's this video where you showed the simulation of how the fluctuations collapse. Right? Do I have this still? There we go. So this simulation, if you don't have dark matter, you don't have enough time to go from these small fluctuations to the very dense objects that we have today. Okay? If you just have normal matter. There's just not enough gravity to cause this collapse, this infall. Okay? So you need extra gravitational pull from dark matter. There's lots of other forms of evidence, like, galaxies are orbiting too quickly to be held. They need to be held in a cluster by extra gravitational pull from dark matter. So I personally think dark matter I think there's no compelling alternative. But for dark energy there is, but I think we know it's there. Yeah.
Еще вопрос?
Thank you very much. Please tell us about 1 or 5 maybe top interesting facts about universe.
Okay. Oh my God. Top 5 interesting facts. I think I've mentioned some of them, hopefully. I think the first one maybe is that we can see the past, right? We don't have to guess what happened in the past. We just have to look very far away, and we can see the past. Another one is that everything comes from random quantum fluctuations, probably. And I don't know, what else is cool? We only understand 5% of the universe. Yeah, I think those are the top few. Okay.
Еще?
Thank you for awesome lecture. It's really good. Why does Big Bang Theory needs an internal tiny dot?
Internal tiny dot. I don't really understand. Sorry, what do you mean?
Singularity.
Okay.
Why does it needs to be smaller than atom?
Well, let's see. You can answer that in several different ways. If you assume that the current laws of physics are correct, then you can prove that there has to be a singularity at the early universe. In fact, that's one of the things that Stephen Hawking was most famous for, a theorem called the singularity theorem that proves that there has to be a point where it goes to zero, assuming standard gravitational physics, like general relativity. So I think that's probably the cleanest answer. Wow. I will give you the paper, and you can work it out. Yeah, I don't know. I guess if everything is sort of flying apart, at some point it has to have been arbitrarily close. Was that? Yeah, it's pretty hard. I mean, I can give you a very hand-wavy explanation. Like if everything is sort of flying apart and it must have been arbitrarily close together, but to get a really rigorous answer, yeah, you're going to have to learn general relativity. All right.
Еще вопрос есть? Переводите вопрос. Так, давайте тогда у кого переводить не надо.
Thank you. And I have probably a bit personal question. Where do you work? Do you work in the desert? Or
In where?
In the desert.
In the desert. Oh no.
No? What's your day?
Oh, yeah,
looks
that's a-
like? You just wake
Okay.
up, go to the telescope.
No. Okay, that's a good question. So, I am part of these experimental teams, but I'm kind of a theorist. I do theory and kind of data analysis. So I don't actually build anything. I could go to the telescopes, but I don't really do that. The desert is too dry. And it is very pretty up there, apparently. I think so what I do is I just go into the office and like yell at my graduate students. Nothing that glamorous. The people who build the experiments, they have a much more adventurous life. They go out to the telescopes and they wear, oxygen masks because it's there's so little oxygen and these are very high. So those are the people who work in the Atacama. The even more extreme people, so there are two locations where people build these ground CMB telescopes on the ground. The other one is the South Pole. So a lot of people will go to the South Pole to build telescopes and to operate them. So, the poor students have to go down there and freeze. Some people have very interesting day-to-day lives. In fact, the bravest people are the people who have to stay with the South Pole telescopes in the South Pole winter. So they are there in the darkness for 6 months, making sure the telescope doesn't break and not seeing any daylight. So there's a lot of work that goes into this. Yep.
Если у вас есть вопрос на русском языке, то задавайте его так, а мы его переведем. Да, это, я думаю, упростит задачу, поэтому я надеюсь, руки еще появятся.
Yeah, great.
На английском? На русском кто-нибудь сможет?
Thanks. Yeah, no, it's great. Okay.
This silly question. What do you think about Elon Musk?
Sorry, what?
Elon Musk. Elon Musk.
Elon Musk. I don't know. He seems cool. I don't know. He sometimes overstates things a bit, but I like him. I don't know.
Elon Musk is a real scientist, in your opinion? Or
He's an engineer.
Okay. Well, I have two more simple questions.
Okay.
You have a great knowledge in galaxies exploring. Well, have you ever seen any paranormal activities? Maybe some unknown flying objects?
No, sadly.
Okay.
I
The
wish.
second question, is Area 51 really exist in America?
I think so, right? I don't think it's an alien base, but I think there is an Area 51. Right? I don't know. This is not what I know. This is not my area of expertise. But.
So you believe in this existence?
Was that?
Area 51 is really exist?
Yes.
Yes. Okay, thank you.
Спасибо большое за лекцию. У меня два вопроса. Первый, как вы думаете, вот это фото, которое представили как черную дыру, это правда?
Okay.
Это правда черная дыра?
Sorry, which picture was showing a black hole?
С черной дырой.
Okay. Not something I showed, but in the newspaper. Yeah. I think it is.
Да.
Yeah, it's sort of showing the shadow of the black hole. The interpretation is a little bit complicated, and there's a lot of, processing that happens, but fundamentally, I would say yes, it does show an image.
Спасибо. Я просто опоздал, может, вы об этом сказали, извините. И второй вопрос. В самом начале вы сказали, что должна была быть материя, которая очень сжата. Откуда она взялась? Она могла взяться вместе с антиматерией, чтобы они аннигилировали, как будто появились из нуля? И если было так, то куда делась антиматерия?
Okay, so, why was everything really dense in the beginning? In some sense, I can sort of explain, well, there was inflation, and inflation happened, But it is true that there's an unsolved question, which is sort of why is there so much matter in the early universe? Why is the original density, even inflation, so high? And I think cosmologists often talk about this as why is the entropy in the early universe so low? So I think there's sort of an unsolved question about the density of matter. It's not clear we know that. I don't know if anyone has proposed any sort of antimatter, matter annihilation idea. There is, though, another big question that's related to this that I haven't talked about, which is why is there more matter than antimatter in the universe? Okay, because you will notice that we are all made of matter, right? And everything, basically, almost everything we can see is made of matter. But most of the laws of physics don't really distinguish directly between the two. So an open question is sort of what made more matter. How did we just basically end up with matter and not equal amounts of antimatter? So I think there are big questions in cosmology related to what you were saying.
Thanks. Спасибо.
Здравствуйте, спасибо за вашу прекрасную лекцию. У меня вот такой вопрос. Насколько я видел на слайдах, сейчас на орбите работает телескоп Планка. Он еще, кстати, работает, ну, в смысле, вы получаете с него данные? Я просто не в курсе был в последнее время. И насколько я понял, да. И еще такой вопрос. А пытались ли вы как-то выводить телескоп конкретно в точку либрации, к примеру, чтобы получать более какие-то такие, ну, чистые результаты в плане влияния, к примеру, магнитного поля Земли или гравитационных полей? Ну, то есть вывести его, допустим, в точку L2, L1, и там уже наблюдать.
Right. Okay. So the first question was, if I understood correctly, is the Planck satellite still operating? The answer is sadly not, as of about a year ago. And the reason it stopped operating is because to make these very low noise measurements, you need to cool your detectors down to a really low temperature, well below 1 Kelvin. Okay, so you have to hold your detectors really, really cold to avoid noise. And so the problem is there's a coolant that you send up with the satellite, and that has run out. So Planck is not operating anymore because it's run out of, refrigeration fluid, basically. The second question is, could we do anything to, I guess, reduce reduce sort of vibrations or contaminations and based on the location? That's sort of what I've understood. So Planck is at L2, right? We put our satellites at the L2 Lagrange point already. So they're already there.
It was in L2 point.
Yes.
Yeah? I hear about Planck, but I'm not...
Right.
Ну, я слышал о том, что его запустили, но, честно говоря, не вникал в миссию, какая конкретно была миссия, поэтому, извините, не знал.
No, it's a good question.
То есть он был в точке либрации L2, да?
Yes, as far as I know, yeah.
Спасибо.
I mean, the ground-based experiments do have to deal with more issues than a space-based experiments because for the reason you hinted at, if you're far out, L2 or somewhere, you have, you don't have the atmosphere to deal with, you don't have, radiation coming in from the Earth or from, you're in a much cleaner environment and it's easier to do CMB research.
Спасибо.
Так, есть ли еще вопросы? Перед вами астрофизик. Как говорил Нил Деграсс Тайсон, типа их там сколько, 1000 на планете. Так что это огромная удача встретить такого.
Спасибо вам большое за лекцию. Мне было очень интересно, и вопрос может быть немножечко не в тему, но он меня очень сильно волнует. Это как именно гравитация влияет на скорость химической реакции? То есть только ли благодаря большой плотности и большому давлению, да, происходит как бы зажигание звезд, да, там, когда газ в общем, сталкивается с гравитацией. Возможно ли такое, что по-разному в разных частях Вселенной, да, могут происходить химические реакции не только из-за гравитации, а вот в общем, темная энергия.
Okay. Right. That's a good question. If I understood it correctly.
Как гравитация?
Oh, okay. Any more questions? All right. So, if I understood your question right, you're asking, does gravity ever directly influence a reaction, as opposed to just influencing it through density and pressure, right? Well, okay. So, does gravity ever influence a reaction? And the answer is yes, it does. But through density and pressure, mainly, okay? So, you know, in a star, gravity will cause the density and the pressure to be very high, and those will influence reaction rates and where the equilibrium is, et cetera. So, by far, the strongest influence of gravity is because of how it affects the densities and the pressures, okay? Now, why doesn't gravity directly affect, you know, say, a chemical reaction? So say I have, you know, molecule 1, molecule 2, and they're coming together. Why doesn't the gravity matter? And the reason is that gravity is really weak, okay? The main reason is that gravity is so much weaker than any other force, right? So most reactions, you know, there's electromagnetic influence, maybe there's a weak force, but gravity is, you know, so much weaker that it can only matter when I have a huge amount of stuff that's gravitating, right? And so one way you can think about why gravity is so weak and probably doesn't really affect reactions, at least to my knowledge. And one way to think about how you can see that gravity is so weak is, you know, the entire Earth is pulling me down, but a small layer of electromagnetic repulsion is holding me up. So a small layer of atoms in my feet can win over the entire Earth through gravity. Right? So gravity is really weak, and I think it doesn't influence reactions that much, I think.
Спасибо за ответ. Я продолжу вопрос. То есть, следуя из этой логики, более сильная, допустим, сила, не гравитация, а, скажем, темная энергия, она могла бы влиять на скорость химической реакции гораздо сильнее. Ну, не совсем так. Ну,
Sorry, a different force, different from gravity, could influence reactions. Is that what you're saying?
Вопрос в том, что может ли какая-то иная сила, помимо силы притяжения, влиять на скорость реакции, так?
Не сейчас, а я имею в виду давным-давно. То есть если какие-то квантовые флуктуации, которые сейчас мы не видим, ну, так повлияли на распределение материи, что спустя огромное количество времени она распределилась таким образом, что получились галактики и звезды, то, возможно, что-то также повлияло на...
Okay. Yeah, so I guess the way I've understood what you were asking, I hope I got this right, was could there be sort of another force that's responsible for a lot of the things that we say is due to inflation or something like that? We have good evidence that it can't just be an extra force that's causing the inflation effects, right? And I think the reason we think that's true is that forces sort of can't travel faster than the speed of light. So there's a certain maximum distance that I can influence things through forces if I don't have inflation, which changes the evolution. And so, but we do see effects. We see correlations on scales that are very large, that are larger than information can travel from one point to the other one. So even if I have a force that's moving, coming from here and influencing that one, I don't think you can explain all the inflation effects with just some new forces or some new sort of causal physics, as we say. So I don't think you can explain everything with new forces. There's a technical answer, and I can. This part of the CMB, the fact that it's flat and not zero, tells you that there can't be forces that are doing this. But I have to explain this more if I want to do it properly.
I have a question. Thank you very much. What do you know about neutrino astronomy? Last news.
I think there are other people at this meeting where we at who know a lot more about neutrino astronomy. I think, I guess last I know about it is that people were trying to, with IceCube, measure the distribution of neutrinos, and they saw that it was coming, it was homogeneous, and there were, it was coming from everywhere. I don't really have any particular news about neutrino astronomy. I am working a lot on understanding neutrinos with the CMB though, and not neutrinos from astronomical sources, but there's actually a background of cosmic neutrinos. Just like there's a cosmic microwave background, there's sort of radiation that comes from the early universe. There's actually also neutrinos that are produced. And so this is something that's also a very active area of research, understanding the properties of cosmic background neutrinos. So something I'm working on now is trying to measure the mass of neutrinos through cosmology. So that's what I know more about, not about the astronomical sources.
Thank you. Есть ли еще вопросы? Есть. Передайте, пожалуйста, микрофон назад.
First of all, thank you very much for the lecture. And I have two questions. First is, do you think the string theory is a serious theory, and can it tell us something about dark energy or something?
Yeah, that's a very good question. Yes, I do think string theory is a serious theory. I think perhaps people thought that it would make more rapid progress than it did over the last 20 years, but I think it's definitely the best theory of how to sort of unify gravity and quantum mechanics. The problem is that, the energy scales and the times, and the situation we're trying to describe is so far removed from what we have, experienced with and even can access experimentally, that it's just a really hard problem, right? And I mean, I personally think it might take 100 years to really figure out how to do quantum gravity. So I think it is, I don't think we're going to be able to prove it right or wrong in the next 10, 20, 30 years. But I do think it's currently probably our best effort, and it might take a long time until we can really understand incredibly high energies that string theory is trying to explain. So, we'll find out in 100 years, basically.
Так, может еще два вопроса? Только короткий. Только короткий.
Что вы думаете о звезде KIC 8462852? Это звезда Табби, которая называется Табби.
Табби Star. И координаты, скажи.
Давайте.
Okay. I think an important thing when you're a scientist is to learn how to say that you have no idea about something, and I have no idea about the star. Like, no idea.
Это я могу пояснить, что это за звезда. Это звезда, вокруг которой астрономы наблюдают непонятные, как сказать, ее заслоняет нечто, то ли пыль, то ли какие-то экзопланеты. Ну, то есть это они совершенно хаотичны и не поддаются систематизации. Именно поэтому она вызывает много вопросов.
Oh, thank you. Okay, oh, interesting, thank you.
Лучше вам взять интервью после этого. Если есть еще хотя бы один вопрос. О, есть.
Есть ли у нас альтернатива теориям Эйнштейна?
Is there some alternative to Einstein's theories?
Yeah, so I think that's a major area of research in cosmology. Yeah, so I think it's particularly motivated by understanding dark energy. The thing that's a little bit frustrating, though, about trying to modify gravity is it's really hard to change the theories of physics in a way that's consistent and doesn't just break internally, or isn't completely ruled out by observation. So typically people think, oh, I can change this little aspect of gravity, but it just breaks, right? In a sense, the fact that you have basically quantum mechanics and special relativity really just means that you can't do very much to change the laws of physics without breaking things, right? So it's really hard to get something that's consistent, that works, isn't immediately ruled out by observations, and that isn't just something sort of that's like as simple as adding an extra particle or something like that. So it's really hard to change. It's on the one hand sort of annoying if you're a theoretical physicist and want to have a great idea, but it's sort of, I think it's quite elegant, right? That the laws of physics are kind of the only way they could be in some cases, and it's very hard to change them. So people are trying, but it's not easy to make something that works.
У меня еще вопрос. Расскажите, как выглядит ваша будничная работа. Ожидали ли вы, что вместо взглядов каждую ночь на звезды вы будете сидеть перед компьютером и считать цифры и пытаться из этого делать большие выводы?
Yeah, there is more sitting at a computer than I thought. I think that's true. But I don't know. I think there's also a lot of... what I like now about being faculty is there's a lot of interaction with people, which is sort of fun. There's a lot of talking about physics. So I really like that. So a lot the teaching, you go into work and you have to teach, and you chat with students, and that's really fun, and they ask good questions. And you meet with graduate students, you have discussions. So I don't, it's not just sitting. I mean, there's a lot of sitting at a computer and a lot of writing emails about various boring things. But I think the chatting with people about science part is still really fun. Yeah.
Thank you.
Yeah.